Hello, this is Professor Gilmet, and today what we'd like to talk about is hypothesis testing. And so, in this video, I'm going to discuss what hypothesis testing conceptually is. And so, we're going to talk about the logic behind why it works and when it works. And I'm going to work through an example that I pulled data from the CDC website on. Alright, so here we go. Therefore, we begin with a hypothesis. It is a hypothesis test after all. And so the first hypothesis is the null hypothesis that we're going to look at. Alright? And so the essence of the null hypothesis is that nothing has changed. Okay? We may think that the GPA of high school seniors has increased, decreased, or just changed. We may think that the crime rate in a particular area has gone down, okay? But what we're going to say is that nothing has changed and that any variation that we see in a sample is due to random fluctuation. And we have seen that sampling distributions do vary, right? They do show a random fluctuation from our previous videos. And so if we talk about the crime rate data, maybe we see 11% property crime in a particular area. Well, if you were to take a sample of 30 days, or if you were to look at the next 2 weeks and you saw that the amount of property crime was 10% or 12%, you wouldn't say that the crime rate has actually changed. You would just say that that was just part of the fluctuation of the sample that you took. Alright? Now, the second hypothesis is always the alternative hypothesis. The alternative hypothesis is our best guess as to how the population we are testing has changed. Okay, so this is it did increase, it did decrease, something like that. And this could be just due to time, the passage of time has changed the population trait, or due to a treatment from an experimental design. We actually did something and we're measuring it, and was it effective? We can never say by how much it has changed with a hypothesis test. For that, we actually need a confidence interval, and that's probably what I'll talk about in the next video or two. Okay? And so thus we write it as an inequality. It's gone up, it's gone down, greater than, less than, not equal to, with the same value as the null hypothesis. Remember, I can't say how much it's changed. So all I can say is that it's greater than, less than, or not equal to that same value that I stated in the null hypothesis. Alright? So, an example will be instructive. Sorry. So let us use diagnosed cases of ASD, which is autism spectrum disorder. And I'm going to pause right here and switch over. The autism spectrum disorder has been measured by the CDC, and so about 1 in 68 children has been identified with ASD according to estimates from the CDC's monitoring network. And so here's the prevalence of autism spectrum disorder, and they measured that in 2010 for 8-year-olds that were born in 2002. And we can see that it is now 1 in 68. Okay, so I actually pulled this off of the website. And so in 2010, the CDC does report that 1 in 68 children in the U.S. are diagnosed with ASD. Some people believe that the rate of ASD has increased due to vaccinations. Okay, that's not necessarily an unpopular belief. This gives us our two hypotheses to write. Hypotheses, I guess that's why the underlining in the green. And so, what are those two hypotheses? So let's go ahead and take a look at them. So here's H naught, right, so this is my null hypothesis right here, is P is equal to 1 in 68. And so as a sentence, what this means is the proportion, that's the P, of U.S. children, that's the population, with ASD, that's the trait, is, there's your equal sign, 1 in 68 from the CDC website. Okay? And so that's what this is right here. P is the population proportion. The proportion of U.S. children with ASD is equal to, is the 1 over 68 is the 1 in 68. And so now the alternative hypothesis, H of A, is that same P, right? The proportion of U.S. children with ASD, but now it's going to be greater than. I feel like it has increased, right? That was what some people believe. So my alternative, I don't know what it's increased to. That's why the inequality. The 1 in 68. And so that means it is greater than 1 in 68. Now note, the value did not change. The P's stay the same. The 1 in 68 stays the same. I just really changed from an equal sign to an inequality between my two hypotheses. All right? And so this is the first step. All right. Now, we can take a sample from the population and test it to see if it's close to the proportion of U.S. children with ASD is 1 in 68. All right? Why does this work? Why can I take a sample from the population, see if it's close to the 1 in 68, and if it is, then I would say, hey, the null hypothesis is true. And if it's not very close to 1 in 68, I would say that the alternative hypothesis is probably true, especially if the sample proportion is greater. All right? But why does that work? Okay? I keep mentioning in the previous videos that we've been laying a foundation for this video. And so we saw in the last couple of videos how even if a population has a trait that is skewed, like the cohabitation example that I did, or bimodal, like the sex of an individual's example, that a sample that is large enough has a sampling distribution that follows the normal model due to the central limit theorem. And so we did two examples where we looked at the central limit theorem, where as long as our sample gets large enough to satisfy the criteria, that the sampling distribution follows that normal model. And in those examples, we saw that as we drew many samples, that the mean, median, and mode was the same as the population's mean, okay, the population's center proportion, but that the variation we saw decreased as the sample chosen was larger. And I actually choose a really large sample for this particular example, okay, but the samples fall near the center that the population center is. The sample center is equal to the population's center. Okay? So that's really important. That's why if I take a sample and it's close to the 1 in 68, then that means my null hypothesis is true. But if it's far away, then maybe something bad has happened. All right? So when I draw a single sample from the population, I expect that sample to follow the empirical rule. 68% of the samples, any sample that I take, should fall between +1, -1 standard deviations away from the center. And 95% of samples should fall between 2 standard deviations away from the center. Therefore, if I draw a sample, only 1 in 20 of those possible samples should be further than 2 standard deviations from the expected center of a distribution, away from the expected center of the population. If it is, that would be unusual. So if I draw a sample, I am 68% sure it's going to fall within 1 standard deviation away from the center, and I'm 95% sure that it's going to fall 2 standard deviations away from the center. and only 1 in 20 would be further away than that. And so that is not what I would expect, and so that would be unusual. Okay? So this means that the next step in our hypothesis test is to make sure our sample meets the criteria for the central limit theorem. If our sample doesn't meet the criteria for the central limit theorem, I don't know that it's normal, and so then I can't use the empirical rule. So this is a really important part of the analysis. So the criteria for using the normal model is as follows. This is our criteria. The members of the sample must be independent. No siblings, members of the same house, spouses. I can assume with the CDC data that there's maybe a sibling or two, but probably no child, not a sibling, is going to affect any of the other in the sample. Okay? If you had a whole bunch of siblings, this would be bad. That would bias the sample. Members of the same house, right? That's going to be siblings. And spouses, right? We're talking about 8-year-old kids, and so they're not going to have significant others. The members must be randomly chosen. The word random should appear somewhere in the description, okay, of the problem or the selection process. Remember, randomization is really important to make sure that the sample looks like the population that we're looking for, that there's no bias involved. All right? Third, it must be smaller than 10% of the population. Now, I actually use the following shortcut formula. I just say 10 times the sample has to be less than, it's thinking, less than the population total. And this is just a reasonable assumption, okay? You're obviously not going to know how big the total is, but you have a reasonable assumption that this is going to be true, okay? And the sample size is large enough. For proportions, because that's what we're talking about for the time being, the number of expected successes, yes, I have been diagnosed with ASD, is greater than 10. And so you can take your sample size times your population proportion, and that should be greater than 10. 10 individuals, 10 members of the sample said, yes, I have the trait. And then, of course, the number of expected failures also has to be greater than 10. And so, remember, failures is 1 minus p. So if I take the number of yeses away from the total number, that would be the number of no's. And so the sample size times the expected number of no's also has to be greater than 10. If these 4 things are met, then the criteria for using the normal model is met, and then the empirical rule is going to be in play. And then I can say whether something is going to be unusual or not. All right? So now, continuing with our ASD example, suppose we take a simple random sample of 100 children and find that 3 of them are diagnosed with ASD. Well, hopefully you realize that if only 3 of them said yes, that we're having an issue with our sample size. But I want to work through the process. Is it reasonable to assume that they are independent if they are random? It is reasonable to assume that they are independent if they are also randomly chosen. So 2, not to, of our criteria are met. Okay? So also 10 times 100 is equal to 1,000 children, which is certainly less than the number of children in the United States, right? So remember, this is going back to my little shortcut formula. 10 times the sample size has to be less than the population total. And so 10 times my sample size of 100 children is 1,000 children, and that is certainly less than the number of U.S. children. So our third criteria is met. Now we need to check the sample size, okay? And so now the sample size times the number of successes, all right? Plugging that in, I'm going to have 100 as my sample size times 1 in 68 gives me 100 out of 68, which is approximately 1.47, which is definitely less than 10. So this shows our sample size is too small. We've got to pick a much larger sample size to get enough yeses so that the normal model is kicked in. This model, because our sample size is too small, could be very skewed. And then we would have to use like Chebyshev's model or something like that, where we put a lower bound on our distribution. And so the sampling distribution may not follow the normal model, as we saw with our previous examples. The cohabitation, when the sample size was like 5, we saw it was very skewed. So we definitely need a larger sample to complete our test. All right. So let's ask 10,000 students from a random sample of elementary schools from around the country. Because remember, I'm really concerned about the number of U.S. children. So I really want to ask at elementary schools where the diagnosis usually takes place around the country. Okay? So the results of the sample reveal that 300 of them are diagnosed with ASD. So I'm keeping the same proportion, the 3 in 100. I just made our sample much, much bigger. Okay? So now we check our criteria and we find the following. All right? So 10 times our sample size is equal to 10 times 10,000, which is equal to 100,000, which is still less than the total number of U.S. children. So our criteria has been met. Okay? And now for successes, n times our yeses is equal to 10,000 times 1 in 68. That's approximately 147 children. Decimals here are not appropriate. We don't want parts of children. Okay? Is greater than 10. Is greater than 10. Sorry about that. So that's definitely met. And then last but certainly not least, our sample size times our no's is 10,000 times 1 minus 1 in 68. And of course, if you put that in the calculator, that's going to be approximately equal to 9,853 children. That's definitely greater than 10, and so that criteria has been met. Quick note, if you take 147 and you add it to 9,853 children, you actually get 10,000. Those two numbers should add up to the sample size. All right, so all the criteria is met, and we can be assured that the sampling distribution is following the normal model. Therefore, we expect that the sample should fall close to the 1 in 68 children value that we saw in 2010. If it isn't, if it is not changed, okay, that's what we would expect. We would expect our samples to fall very close to the 1 in 68 children value that was measured in 2010 if it has not changed. That's our null hypothesis right there in a nutshell. So this basically leads us to the next step, all right? And we're ready to do our calculation to see how far our sample falls from the expected center, from that population proportion of 1 in 68. A long time ago, this is where we would focus almost all of our attention because it was difficult and complicated to do the calculation, okay? But nowadays, with StatCrunch and TI-84 calculators and Wolfram Alpha, this is actually probably the easiest step. Okay, it's just kind of a plug-in to your software of choice and have it pop out the answer. But it does require that we calculate a z-score and enter it into a normal calculator to find the p-value. So I'm going to work through that process. All right. Note, the p-value is the probability of observing a sample of this size. Remember, as size increases, variation gets smaller, so the size of the sample is affecting things. With this many or more successes, okay, so we're talking about greater than or less than the number of yeses that we saw if the null hypothesis is true. And remember, we're assuming that the null hypothesis is true through this whole process until we have evidence of the contrary. All right, so that's just what the p-value means. So now going back to our example for diagnosed ASD, right, I just want to remind you that the p is 1 in 68, which is 0.0147, and that's the proportion of U.S. children diagnosed with ASD. And then we've got p hat, that's our 300 out of 10,000, our 300 yeses out of 10,000 students asked, which simplifies to 3 in 100, which I guess maybe I should actually say is equal to 0.03. And so this is the proportion of the sample that's why the little hat, of U.S. children diagnosed with ASD. So this is what I believe the population proportion to be, but this is my sample proportion right here. Okay? And so now the standard deviation of my sample proportions, right, because I'm looking at a sampling distribution, will be equal to my population proportion times 1 minus my population proportion divided by my sample size, take the square root. Now, I choose to use 1 minus p. A lot of books use q. Don't be fooled. Q is just 1 minus p. And I think there's some nice conceptual reasons to use 1 minus p. Plugging in our values, remember the... let me make this a little bit bigger because this is getting kind of small. Remember the 0.0147, that comes from our p. 1 minus 0.0147, again, that's our p. And the 10,000 is our sample size. And so that's going to be equal to, if you put it all into the calculator at one time, using parentheses as appropriate, you get 0.0012 is the standard deviation of the sample distribution. Okay? And so that's how much variation we would expect to see in samples if I have a sample size of that large. And so now we're ready to find a z-score for a sample of 3%. And so that's going to be my p hat minus my p divided by the standard deviation of my sample proportion. And so again, if I plug this into the calculator using parentheses in the numerator, what I get is 12.75. Okay? Now, this means that our sample is almost 13 standard deviations away from the expected center of 1 in 68. So we will use this to calculate the p-value. Although hopefully your gut is already telling you that 13 standard deviations away is not very likely. In fact, it's so unlikely that when I put it into the StatCrunch calculator, to 7 decimal places, it actually told me that it was 0. And so the p-value is essentially 0. If you plugged it into Wolfram Alpha or a TI-84 calculator, it might actually give you a value in scientific notation that shows you that 1 in 10 quadrillion samples would be that far away. But this basically means that the probability of seeing 300 or more children diagnosed with ASD in a sample of 10,000 is approximately 0. And what's really making the z-score so large is the fact that my sample size is huge. So this is definitely statistically significant, but in another video we may talk about whether it is an important difference or not. If the true proportion of U.S. children diagnosed with ASD is still 1 in 68. All right? So now this brings us to the last step. Therefore, the last step is to actually write the conclusion. What does it mean? Okay? So in the conclusion, we usually compare the p-value to the level of significance for our circumstances. And so the level of significance is denoted by the Greek letter alpha, and that's the symbol for alpha, and it is typically one of 3 values. Based upon circumstances, I may choose to have an alpha of 0.10. I saw this a lot in my early educational career. In my current studies, I actually see it less often, and I'm kind of grappling with why. For my class, most common in many disciplines is alpha is 0.05, and I hope that you can see the reason why that's the most common there is that it's 5% of the population. And so if 2 standard deviations is 95% of samples, then 5% of samples would be considered extreme. So this is usually one of the most common. However, because of one-tailed tests, because sometimes we're wanting to try to avoid doing harm, sometimes you want to be really strict and minimize a certain type of error, and so you would make alpha equal to 0.01. But you would know, this would be the understood standard in your discipline for a certain type of experiment, for a certain type of observational study. This criteria, as you get into your field, would be very well understood. But for most introductory stats, for most problems, as you're getting started, 0.05 is the most common. And it is because that means that the sample is more than 2 standard deviations away from the center. So when comparing, we have two choices, right? Because remember, we're comparing the p-value to our level of significance, to our alpha, okay? And so we basically have two choices. We either reject the null hypothesis because our sample provides evidence that our alternative is a better choice, so that's one option, or we fail to reject the null hypothesis because our sample does not provide us with evidence that the alternative is a better choice. Okay? And so the comparison with its conclusion is as follows. If alpha is greater than the p-value, this means we should reject the null hypothesis in favor of the alternative. The sample is simply too far from the assumed value to believe it is a random fluctuation. Remember that idea of a random fluctuation came back very early in the video. Okay? So if my p-value is smaller than alpha, then my sample is too rare, too unusual to believe that it is a random fluctuation. Alright? And this is our evidence. This is the evidence our sample provides. Okay? Now, if alpha is actually smaller than the p-value is actually fairly large, that means that it's fairly probable to get this type of sample. And so if it is fairly probable, we would fail to reject the null hypothesis in favor of the alternative. Okay? Now, we're not going to say the null hypothesis is true. Okay? We can't say that. We didn't actually test whether it was true or not. We just tested whether our sample provided evidence that it was far away. Okay? We can't really test the truth of the null hypothesis, and we're going to talk about that with in the next video when we start talking about errors and the type of errors that we could commit. So the sample actually falls close enough to the assumed value to believe it is a random fluctuation and not a true change. Okay, so we don't have enough evidence. So to conclude our example with the ASD, we will write the conclusion, and I've written it here. We reject that the proportion of U.S. children diagnosed with ASD is 1 in 68. So this part of the sentence right here, that's the null hypothesis. We have strong evidence, right? The evidence of our sample that we took of 10,000 with 300 children that had ASD, that the proportion of U.S. children diagnosed with ASD is actually greater than 1 in 68. So remember, the U.S. children diagnosed with ASD greater than 1 in 68, that's our alternative hypothesis. We're rejecting our null because we have evidence in favor of the alternative hypothesis. Now, because there are different levels of alpha, okay, because there are different levels of alpha, because if I have 0.06, I may decide to fail to reject, but if I have 0.04, I would reject, but those are close to this 0.05. It's a very good practice to actually provide the p-value so that you can tell your reader, your audience that's looking at your study, how strong the evidence is. So leaving off the p-value is actually a red flag that something bad is going on. All right? So now, does this prove cause and effect? Okay? Well, only if we conducted an experiment, and then only to the population represented by the participants in the experiment. Okay? So going back to our example, the problem stated that people believe that vaccines are the cause of the increased autism spectrum disorder. while we did determine that the rate has probably increased, there is a chance that our conclusion was an error, which we'll discuss later. We actually don't know the cause because this was an observational study. I was just looking at what is naturally occurring. I did not manipulate a variable and actually cause a randomly assigned group of children to be vaccinated and observe the ASD rate and have a randomly selected group of children not receive vaccinations and see how much ASD was there, right? That would be an experimental design. Give vaccinations to one group, don't give vaccinations to another group, see if there's a statistical difference in the amount of ASD that occurs. Okay? I should also note that I totally made up the sample data for this problem. I did not do a huge study of 10,000 students and found that 3 of them have ASD. So in point of fact, the rate of vaccination has been declining while the rate of ASD has been increasing, and you can check that out because that's published by the CDC. So a hypothesis is a hypothesis is the increase is due to better diagnosis of ASD, and the CDC actually talks about that. So be careful about what conclusions you draw. Yes, the rate of ASD has been increasing, but unfortunately the rate of vaccination has been declining, and so that's not a cause. And we can't conclude that because this was an observational study. All right. So this concludes the major ideas behind a hypothesis test, how it works and why it works, and that makes us very, very happy. I know this is one of my longer videos, but hopefully it really broke down the how and why of hypothesis testing. Okay? And so in our next video, we'll go into why our conclusion might be an error and how we might minimize the 2 types of error. But until then, I hope you enjoyed this video, and have a great weekend.